How's that sound? Okay, so first of all, I just wanted to thank you so much for the opportunity to come and speak with you. This is very exciting for me to do these kinds of events. It's really injects a lot of positivity and good energy into my time doing astrophysics. And I had the opportunity to come and speak to you a couple months ago, but I actually got the flu. And so I was very, very sad about that. So I'm very grateful to Laurel for reaching out with another opportunity. Okay. So let's go ahead and get started, and we're going to talk about how we make heavy elements in general, how heavy elements are made. They're made in astrophysical environments. So we're going to start out. Okay, the first thing that I want to do to give some sense of scale, to give some sense of where we are relative to the things that I'm going to be speaking about, is this cute little video that essentially is going to start out on human scales, and then we're going to zoom all the way into this tiny particle called a neutrino that we will talk about along the way, and then zoom back out to galactic scales. So here we go. All right, we're going to start zooming in. We're past human scales. Now we're down to an ant size, LCD pixel, infrared wavelengths, blood cells. Keep going. DNA, keep going. All the way down. Now we're at the atom. Keep going. Oh, wow. All the way down to a gamma ray wavelength. Keep going. An electron, a nucleus. Let's keep going. All right, there's something that I don't want to explain, and here we are. And here we are at the neutrinos. Okay, rest of these tiny, tiny little particles that so many of them are produced by the sun, for example, that they're passing through you, millions of them passing through you right now, for example. They just interact very weakly. So now let's zoom all the way back out. All right, we're not even to human scales yet. Okay, here we are. Now we're human scales. Now back out, out, out. Neutron stars. Okay, now we're getting California, different planets, the Earth. Keep going, keep going, keep going. And eventually we will get to galactic scales. Okay, so the point of this is that what we're going to do is consider how even the very, very smallest things can affect what's happening on these very, very large scales. Okay, so it's all quite connected. Okay, so let's go back to my title, and it's essentially a quote that I believe many people have heard from Carl Sagan. We are made of star stuff. Our bodies are star stuff. There are pieces of stars within us all. So if you take a look at this beautiful figure, you can see that the percent of human body ingredients, things like oxygen, things like carbon, things like nitrogen, these were all made in stars. You see iron here as well, very important, obviously, for things like our red blood cells. That is something that's going to be made in a more elaborate process a little bit than not every star can produce iron, for example. But when we get to the heaviest guys, like gold, for instance, we just mentioned alchemy, right? When we're talking about gold, that's even heavier. And so that's actually going to require even more exotic events. So we're going to work our way up to that over the course of this talk. So the first thing that I want to do is take this kind of fluffy, pretty quote from Carl Sagan, who was more in science outreach. He was, of course, also an observer, but still. So this is a very fluffy quote, and I'm going to pull a quote directly from a paper that's one of the seminal early works in nucleosynthesis studying how elements are made. This is directly from a paper, Burbage, Fowler and Hoyle, 1957. These are the Burbages, and right here, these are the Burbages, and that's Fowler right there. Hoyle is not in the picture, but something I want to note right away, first author of this work in 1957 was a woman, Margaret Burbage, okay? Now, what they say in their paper, I'm going to move my cursor. Oh, it's not my cursor. It's okay. The element composition of our sun shows signatures that multiple distinct astrophysical processes contributed to the content of our Milky Way. So in other words, it's not just stars that are doing this. It's not just this type of star, that type of star. There's multiple different types of processes that are going on out there, and that is what's producing the elements. So this is what has created the field of study known as nuclear astrophysics, in which I work. And you can see here the periodic table of elements, color-coded by where we think some of these elements are being produced. So if you take a look, you have some of these lighter ones from the Big Bang. Then you have things like stars are in there, but you see all this orange right there is from something called the rapid neutron capture process that I'm an expert in. And this is where we're getting the heaviest species. But before we get there, let's step up, right? So this is the periodic table. Everybody's familiar with the periodic table, but let's go over and make sure that we understand what we're seeing here relative to the different building blocks that I just showed in that movie. So for example, a carbon atom is going to be 6 protons, 6 neutrons surrounded by 6 electrons. Once you get to something super heavy like gold, okay, I shouldn't call it a super heavy because there are super heavy elements technically, but something heavier like gold, here you see it's got a very different structure. It's much more complicated. It has many more protons, many more neutrons, etc. Now I'm going to change the periodic table to the version of the periodic table that nuclear physicists look at, and that is called the chart of nuclides. So I've gone ahead and I've labeled now where those elements from the periodic table have found themselves on this new chart. So this chart has proton number increasing on the left, neutron number increasing on the right, and that's effectively how we look at all of the different nuclei that can be formed, okay? So a given element is at a given proton number, but it can be very neutron rich and have an isotope that's very neutron rich, for example. And as you can see here, at some point, we run out of nuclear data. We actually don't know the properties of these species at a certain point. We hit the edge of what we know, okay? So that's just to gauge and what we're going to be looking at, the landscape that we're going to be looking at here, and how it compares to the periodic table. Now, I mentioned the lightest elements are being formed by Big Bang nucleosynthesis in the very beginning of the early universe. But Big Bang nucleosynthesis primarily just makes hydrogen and helium. You can see some of these transitions here about exactly a proton going to deuterium, to tritium, to helium, to barium, things like this happening. It's a very small amount of elements that you can play around with within Big Bang nucleosynthesis, but nevertheless, just dominantly you're making hydrogen and helium. That's where these things are coming from, okay? Now let's talk about stars. So I'm going to work our way up to those heaviest guys that I tend to study all the time, like gold, okay? So let's start with just stellar fusion. So essentially what's happening, why our sun is not just collapsing on itself, is because of nuclear physics reactions. You have a bunch of hydrogen in the sun that can fuse into helium, and this is actually a process that releases energy. Therefore, it can just happen without you having to put any energy in. So this is something that can dynamically happen, and when it happens, it's going to produce some external pressure on the environment. You release energy, it creates a pressure, and that can counteract the gravity and keep the star from collapsing on itself, okay? So that is essentially the key idea about stellar fusion counteracting gravity with different nuclear reactions. Okay, now, as I mentioned, the sun is mostly hydrogen and helium. Hydrogen is basically a proton and an electron. So oftentimes when we talk about fusing hydrogen right here, we call it the PP chain. All right, so you can fuse hydrogen into heavy hydrogen, which can then fuse into helium, so on, so forth. This is the dominant thing going on in the sun. All right, the sun is mostly hydrogen and helium. This is the primary energy source for the sun, is the PP chain. This is where the energy is coming out. Now, you may say, how do you know that? Okay, well, I'll give you one piece of evidence. Do you see this little new right there? There's your neutrino that is coming out of this reaction. So neutrinos are produced by the sun, lots and lots of them. So much so that you can take a picture of the sun in neutrinos. And that is what you're seeing off to the right there. That is a picture of the sun in neutrinos. Another thing down here is the flux of neutrinos, how many we have coming at us at a given time over a given surface as a function of energy. And you can see the dominant thing contributing neutrinos is again that PP chain. So there you go. You can see this would be what we would see from the PP chain, and indeed it's what we see from the sun. So that is what's going on in our sun. Okay, now let's push this even more. We can just keep pushing and pushing. At some point, you can fuse hydrogen into helium, you can fuse helium into carbon, and so on and so on and so on. You just keep going down. This produces in an idealistic kind of visual of all this, what they sometimes call the onion structure here, where you have different regimes where you're primarily putting hydrogen into helium, helium into carbon, so on as you go down, okay, within the star. Ultimately, however, you get to iron, and you can see all of these different transitions from going from hydrogen to helium or going from helium to carbon, very different timescales. This is more than 1 billion years right here, something like 1,000 years to fuse carbon. And then once you get down to something like iron, you're less than a second all of a sudden. Now, why is that happening? Well, what's happening here is once you get down to iron, this whole idea that you can fuse nuclei and then create energy kind of stops. Because what happens is that iron is specially bound in a specially way. It has what we say, the highest binding energy per nucleon. Therefore, anything after this, anything heavier than this, is actually going to take energy in order to fuse it. You have to put energy in now in order to fuse it. So this fusion process of where you can get heavier and heavier species breaks down at some point. You can't do it anymore. So you tend to get stuck at iron here. That's why you get an iron core of these more massive stars. Then that iron core can collapse. And when that happens, you have the material react to this. There's a shock breakout that moves through the star, and an explosion moves through the star after that, and the layers can come off. You can see light from this, et cetera, et cetera. So this is called a core collapse supernova when something like this happens. Now, can core collapse supernova make the heaviest elements? I said I want to talk to you about the heaviest elements, the gold, right? Where's that gold coming from? In the past, actually, prior to about 15, 20 years ago, that was the thought that core collapse supernova could have some special types of, we call them winds, but basically it's just some kind of movement of material within the environment that can then have the neutrinos that are going through that environment interact with the material, make it very neutron rich to the point where you can start capturing those neutrons to make heavier and heavier elements. But that was a potential picture a couple years ago. Now, modern hydrodynamic simulations of core collapse supernovae no longer support that you could get to the heaviest species through core collapse supernovae, okay? They just don't get neutron rich enough. So in other words, you can look here at what you would expect for the elements that you produce from a core collapse supernova as a function of atomic number. Atomic number is just proton number. So you see about here is iron. These things make a lot of iron for the reasons I just explained. And it's really only going up to silver if you're lucky. Gold is much, much beyond that, okay? So it doesn't appear to be core collapse supernovae, ordinary core collapse supernovae, given our most advanced simulations that we use nowadays. Now, how do we even know that there are supernovae? How do we know that this process even happens where things explode? Well, first of all, we have seen these things go off. before. And one of them in particular is special within our community of nuclear astrophysics. It's supernova 1987A. So with this particular event, we call it one of the first multi-messenger astrophysical events. That's because from this event, we detected both neutrinos and the light that was coming from this event. So when you have these two distinct messengers, so to speak, you have a lot of things that can help you with modeling now. You have two distinct things that can help you with modeling. You can see here that the light curve that they show has some nuclei on it, things like cobalt and stuff mentioned. That's because that the way that the light shines and how that light curve goes depends upon the decay of any radioactive isotopes that are present, okay? So this is the kind of multi-messenger event that can tell us that these things are happening, and these what was observed matched with the models at the time decently, but there's of course some debate. So there's something like 30 neutrinos that were detected from this event, but there's been like hundreds of papers on this event. It's quite interesting. Okay, now how else? Yeah.
You could just take a look at that. You said there's a light curve.
Yeah.
Okay, but I don't know a light curve of what, and why do you plot nuclei on the light curve?
Yeah, so this will become more and more obvious as it goes. It's literal light that's coming out of the environment. However, the way that the light is absorbed or emitted within that environment, it does something to the magnitude of that light as a function of time, okay? So then it's directly connected to what nuclei are present. Okay, so this,
some of light emissions
yes.
and different elements or nucleotides produce different shaped curves. And that's why you're bending it.
Yes,
Okay.
exactly. So another way that we know that supernova are a thing is that we observe their remnants. We've seen these types of explosive gases that you can see they're inhomogeneous at times, and so on and so forth. So we can look at their remnants. That's another way that we know that they're supernovae. Okay, so we just talked about what can happen in a star and how you can go all the way to iron and fuse all the way to iron, but that depends on your mass. That depends on your stellar conditions, whether or not it can go all the way to iron to begin with. So this is just a chart of if you have mass and it's getting ever larger, what the ultimate fate of the star will be. Okay, so we have things like ultimately you make a brown dwarf, a white dwarf, a neutron star, a little bit here. So what about our sun? Our sun will someday be what's called a white dwarf, okay? So what is a white dwarf? Essentially, this is one of those systems that as you're fusing down, 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 it just doesn't have enough pressure, it doesn't have enough mass to it to keep going with that particular argument. And therefore you stop at something like having carbon and oxygen or oxygen and neon. And so they often call these carbon oxygen white dwarfs, oxygen neon white dwarfs, et cetera, et cetera. So that's what a white dwarf is. Now these things are very, very dense, as you can imagine. But to give you a number, it's something like 200,000 times as dense as the Earth with about the same radius. Okay, so that's pretty dense. Okay, so now the next thing, this is not listening to me, that I need to explain is a neutron star, because this is going to be of relevance to our R process discussion. So what is a neutron star? This is something that's about a 12-mile diameter, about the size of Manhattan, but is 1 to 2 times more massive than the sun. It's as massive as the sun or double the mass as the sun, but in this kind of volume. So you can imagine this is just a rendition relative to Vancouver. No, there was never a neutron star over Vancouver, thank goodness. But nevertheless, this is, you can see in this very tiny area, you're packing the sun or 2 times the sun. That leads to numbers that are something like if you could take 1 teaspoon of a neutron star, it would be the mass of 700 Great Pyramids. That is how dense these things are, okay? So that is a neutron star. Okay, so now that I've set you up with some of the basic ideas about how elements are made in different environments and different stars, I want to zoom back out and look at the big picture, right? So nuclear astrophysics is obsessed with the question, where and when were the elements we see in stars produced? Now, if you look at a star like our sun, you do see uranium. You do see thorium, you do see gold, but it's not being produced there, I just said, right? It's just hydrogen and helium mostly is what's happening in the sun. So how is it the case that we can look at stars and see these elements come through? Well, what is actually happening is that you're going to have some kind of event that produces heavier elements, something like a massive star, a supernova, something like this. And then they will eject this material into the interstellar medium, which will then mix. A star will form in that medium, and then the process can continue. Okay, so this is why we can look at stars like our sun or other stars. We do look at other stars as well, and look at their element content and try to figure out what produced. This was a more simplified picture, okay? We just had supernovae on here, but I just told you supernovae can't really make the heaviest species according to our latest models. So there are other things. There's more exotic things that can happen now. Things like supernova with extremely high magnetic fields, which we call MHD supernova. Things like neutron stars will merge with each other. And this is a really cool one that we're going to talk more and more in depth about. You can have white dwarfs accrete from a stellar companion. You can have white dwarfs merge. So all sorts of things can now happen with these remnants that as well could produce elements. So we're going to focus on these heaviest elements that are produced by what I've already said, the rapid neutron capture process, our process for short. And right now here are some prospective places in which they might happen. This one is confirmed, as we will talk about, but these are prospective candidate sites at this point. But we're going to get into talking about our process and how you make the heaviest elements. So to start discussion, let's look at the solar abundances and that I mentioned in the beginning, which we belovedly call B squared FH. So what did B squared FH have to say about the heaviest species? I really love this quote. You can see right here in the stellar pattern, there's your iron peak. No surprise that we've got a ton of iron, right? Okay. But you can see these are the heavier elements right here. So here's the quote. It has been generally stated that the atomic abundance curve has an exponential decline to A of 100 and is approximately constant thereafter. Although this is roughly true, it ignores many details that are important clues to understanding heavy element synthesis. So yeah, you look at this and it's just falling off and becoming a small amount, but there's a lot of structure in here that's heavily connected to the nuclear physics and the nucleosynthesis that's going on. So let's take a closer look at that. Let's go to this proton, we call it the NZ plane sometimes. This proton number, neutron number plot that I showed you from before of the chart of nuclides, you can see that this is where we have some information experimentally. This is where the R process is synthesizing material well outside of what we have experimental data for. So we have to rely on theory. Nevertheless, there are some things that we know. So we know that there's something called magic numbers with neutrons and protons. When a nucleus has this amount of neutrons or protons, it's especially stable. Okay, so at 50, at a neutron number of 50 is one of those cases, at a neutron number of 82 is one of those cases, and at a neutron number of 126 is one of those cases. So as we capture neutrons to go up and up and up and make these, we tend to get stuck or pile up at these areas where we're especially stable of these magic numbers. So if you didn't already know this from a nuclear physics perspective, the cool thing is that the sun could tell you. So let's go ahead and show that. I'm just going to re-put up the solar abundances, and then I'm going to rotate it. And then I'm going to just connect with some arrows. So do you see these peaks right here where you get enhanced production of these elements or of these isotopes, basically? And that is directly coming from this type of pileup. We call that the second peak. So over here is the first R process peak. This is the second R process peak. This is the third R process peak at this n=126 shell closure. So this is just to show you how structure from nuclear physics is coming through and framing your abundances. And so you do have lots of clues to look at. Okay, so that was just some zoomed out ideas of nuclear physics imprinting on your observable. All right, now we talked about fusion quite a lot at the beginning, but when we get to some of these other processes that are going on in astrophysics, much more complicated than just fusion. You can have captures of neutrons, which is key for this rapid neutron capture process. You can have captures of protons. You can have captures of alpha particles, which is actually just helium. It's helium. Okay, I don't know. It's just a historic thing that we call it alpha. But anyway, you can have decays such as beta decay, where you have essentially, you can see on this chart right here, you have where you're converting a neutron to a proton. You can see that you're doing that. You can neutron emit. You can alpha emit. So you have these types of decays that are going on, and you have fission, where you can have the nucleus just be way too heavy, way too unstable, and that thing breaks. Okay, so there's a lot of different nuclear processes now that we have to look at once we're moving into these heavier and heavier regimes within astrophysics. So there's a lot to put in. So I'm going to show you how we now model the R process specifically, now that you have some background in how nuclear physics inputs, the kinds of nuclear physics that goes in. So things like nuclear masses, things like their beta decay rates, their alpha decay rates, their neutron capture rates, how they fission, all of these things are things that we put into what we call a nuclear reaction network that tracks all of these reactions and tracks how the abundances of elements change accordingly as a function of time. We combine that with density temperature profiles from simulations, those hydrodynamic simulations that I told you about, where they model these kinds of events. They put in little follow the temperature, and then we can run it through our nucleosynthesis codes and figure out what's produced. So we have to combine that, all these sets of information, into something that looks like what you're about to watch on the right. So you're going to watch a movie of the R process happening from something like a neutron star merger ejecta condition, okay? Up top is the solar abundances again, but here I've subtracted out other things that aren't our process or believed to not be our process, the slow neutron capture process. So you can see again, that's the R process second peak, that's the third peak. And just for some assistance in where elements are, here's where silver is. Here's where gold is in that third R process peak. Then we have these lanthanides and these actinides. Actinides are the ones that fission. We'll get back to lanthanides a little bit later. Now down here is the NZ plane. Yet again, you're going to watch things synthesize in real time, but they're going to be color coded by the dominant reaction channel that they're undergoing at the moment. So pink for neutron capture, blue for beta decay, red for neutron induced fission, and so on. So I'm going to go ahead and play. You can see at first we start out in some kind of equilibrium, then we're breaking out of that equilibrium, and we're going to move up. You see the elements being made up there. At some point we hit a wall up here where we've gotten really, really heavy and we start to fission down, okay? And now we're creating these because we got pushed all the way up through fission as we're decaying back to stability. These black boxes are stable nuclei, okay? So that's the R process in a nutshell. That's how it's all working, all right? So we do this obsessively. We do these simulations with different nuclear physics, different astrophysics, obsessively, and compare to this stellar data to try to figure out what astrophysical sites are doing this, and what is the unknown nuclear physics that we may be able to extract from the astrophysics, or that we need the experiments to go and measure. Okay, so now that we have a sense of the R process, let's talk about a particularly special R process site, and that is neutron star mergers. So before I gave you an example of a multi-messenger event, this supernova multi-messenger event, right, where you saw neutrinos and you saw light. Nowadays, we have gravitational waves. If you guys haven't heard of LIGO, a gravitational wave detector, I very much encourage you to look at that, and also invite Jess MacGyver from UBC. She's a LIGO person and she's fabulous. But anyway, we have gravitational waves now that we can detect as well. So there was an event, GW 170817, in which first the gravitational waves were detected. And then later they turned their scopes, and something like 1/3 of the community followed up on this merger event. Lots and lots of telescopes were turned to this merger event. So you can see as these things approach each other, you can see the gravitational wave is going to get more and more, the frequency is going to get just stronger and stronger, as you can see from this here. Then they're going to merge, and then we get some kind of light coming out of there. So you can see that down here, right here, this little blurb here is actually the emission from the event that happened, the neutron star merger event that happened. This was observed in ultraviolet, infrared, radio, gamma ray, X-ray, optical, everything. It's quite amazing. So this, you can see from the calling card here, 170817, happened in 2017, not even 10 years ago. So we are obsessed with this event within my community. We analyze its output all of the time. This is a really big one for our community, okay? Okay, so now we've seen that we have some evidence, all right? There was a neutron star merger that happened. The gravitational wave told us it was a neutron star merger. We know it was a neutron star merger. Then we turned our telescopes and we saw light come from it. Okay, great. So what does that mean? Well, let's take a look at what you might expect from the light if you had heavy elements produced. So on the left, you see a model. And what this model is telling you is the luminosity, how much, essentially the magnitude of your light that you're getting, that's coming through, that you're receiving, and how much does that change as a function of time if you had more and more and more and more of these lanthanide elements present. You see these orange elements. So this is this F block of the periodic table. Essentially, it's on the F block because it has an atomic shell open to it where electrons can go, where it can capture different photons. So it makes things kind of opaque to photons. That's why they have what we call high opacity if they're around. And that's why it has such an effect on this light curve, all right? So essentially, it's either lanthanides or actinides that can do this kind of thing. Modify your light curve because you have a bunch of them around and your light's got to get through all of this material, okay? But lanthanides are easier to get to, so we think we know at least lanthanides were produced. But nevertheless, here's the model. Let's look at the observation. Here's the observation. So you can see this is exactly what was predicted, that we have kind of a different shift in the light curve towards this sort of 5-day period here, okay? We have this sort of shift in the light curve, and we also have the spectrum move to the infrared. You can see exactly right here that we had at an early time something that was more blue, but then at a later time right here, you see that bump and you see that we have a domination from the infrared. So this is the evidence. This is why this event is a huge deal for our community, because it's pointing to the fact that it seems like these neutron star mergers at least make lanthanide elements. We did not have any real-time evidence for our process until this happened, okay? Okay, so that was lanthanides, and I said, hey, so it looks like at least lanthanides were produced, but actinides could also produce this high opacity. So how do you know they weren't around? Frankly, we don't. That is something from that event that we do not know. We know we at least got to lanthanides. We don't know about actinides. But interestingly enough, I keep bringing them up because they're titans of the field. The Burbages back in the 50s had this idea that a very heavy fissioning nucleus, californium-254, could be produced in supernovae, and then it would modify the light curve. They actually thought that that was the reason for the shape of the light curve from a supernova in the past. Nowadays, we know that it's not. It's more like nickel and cobalt type of things, but nevertheless, that's what they were thinking back in the day. I told you those supernovae can't really get up here. You can see from this chart in the NZ plane, this is where a bunch of things happen, a bunch of nucleosynthesis processes happen. They're not really getting up to californium. But as you can see, this R process that kicks up, and you even saw the movie, can get up there. So we put out, after GW 170817, our group pointed out that if this species was made, you would get a very, very different signal from the emission here. So as you can see, here's what it is with californium-254, without californium-254. So it can be the difference between detection or non-detection for something like the JWST telescope. All right, so this is something that we did not see from this event just because of the nature of the event. It went behind the sun, la, 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 la. We don't know from this event about californium, but it's something that we pointed out that if future events happen and we see their light, we could have a smoking gun signal that we do in fact get up here, okay. Now, we talked about we don't know if we got up here. We talked about we know that we got down here, but gold is here. So if you ever, after this event, read some kind of science magazine or article that said, whoa, now I know where all the gold in my ring comes from. Well, you're jumping the gun because we have confirmation that we're down here, but gold is up here. And as a scientist, I like more direct evidence of things. I don't want something that's just like, oh, we made it there. We probably made it up there. No, we need something that's a little bit more ironclad. So something that we found within the last couple years is that there is a nucleus here that does interesting things that could tell you whether or not you reached something like gold. So this is thallium-208. It's a particular nucleus that when it decays, it emits a gamma ray line, a gamma ray at a particular energy. And this is known very well in things like nuclear medicine, in things like geology, but it actually had never been discussed in astrophysics. So we pointed out that this particular species could in principle do something, but it's not because we were geniuses and we knew that this is in all of these other sciences. Why not here? What actually happened is we did a very high fidelity calculation, the most careful calculation we could with the nuclear physics, and this is what we saw. So we've gone ahead and put thallium here for you, but you can see that this is what we would predict to be the observed spectrum with thallium versus without thallium. So we see this very persistent bump. It shows up around 12 hours. Then it's going to be there through like 4 days or so. Then it's going to go away for a little bit. And then on the order of years, it comes back. So this is something that's prominent, and it's even more, you see these gamma ray lines. These are gamma ray lines, emission at a particular energy. These are even more like a fingerprint than something like just saying, hey, the light curve looks a little bit higher here because it's got lanthanides. These are a fingerprint. So gamma rays are something that can give you a lot of information about the specific composition, and thallium is a particularly interesting one. So we discovered thallium through just doing high fidelity calculations. digged into the literature and discovered that it's really well known in other fields. So we went ahead and put this out. And what we realized is essentially this is being produced through this decay chain, but you don't have to wait for the things to decay that take a really long time, like thorium. You're dynamically populating things along this decay chain as you do the R process. So that is how we're producing this at multiple different times. So we went ahead and looked, okay, this is an example when we just look at the flux within the energy range of the thallium 2.6 MeV, and we try to look at what else is competing. We really went through our calculation to do all of the legwork to check all other nuclei that might compete in this area and make sure that nobody else is shining through, or if they are, they're not shining through on the thallium timescales and disrupting our signal. So you can see here, this is our thallium only, this beautiful turquoise line. You can see the total without thallium just totally drops off here. Okay, so it truly is just thallium that's producing this kind of signature at the times that I showed you. And on the in-between, other nuclei can show up, but it's not at the time thallium is being produced. Okay, so that's something that's prospective. This californium, this thallium, these are all prospective things that you could potentially see from a future event to get a better handle on what was produced. Now, something else that's really important and interesting that LIGO can do, these gravitational wave detectors can do, is tell you how frequently these types of events occur. So how frequently do we have neutron star mergers? How frequently do we have neutron star black hole mergers, for example? And this is something of direct relevance to us if we want to know if we have enough neutron star mergers to explain what we see in our Milky Way. So after GW 170817, LIGO did put out a rate, a measured rate that they had, and here it is. All right, so what we did was to go ahead and run a bunch of nucleosynthesis calculations with very different nuclear physics inputs. Things like different nuclear masses were put into the calculation, and you can see the range on predictions that we got. We propagate that through to see how much, so what does your neutron star merger rate have to be in order to be able to have this type of synthesis be what's responsible for the solar, for what we see in the Milky Way, for example. So you see, we do have quite a band here from these nuclear physics uncertainties as compared to what they pin down for the merger rate. Now, there have been a few more events since then. We haven't seen the beautiful light from them like we did. They were too far away, but we can still update this rate accordingly. So updating this rate, you can see we moved down a little bit. We're getting less of them than we expected. So this is something right now that we're trying to understand. But nevertheless, you can see that we're moving into a part of the space here that's away from the nuclear physics uncertainties. So we're trying to look at how can we narrow down this nuclear physics band as we're narrowing down the LIGO band to really get a solid idea of if neutron star mergers are the source. So enter experiment. I am at Triumph. Triumph is a facility, if you have never been there, that is full of beautiful experimental halls, like everywhere. It's a rare isotopium facility where it produces some of these really heavy species, and then they study and measure the reactions, all these things that I told you we don't know, that we need to know, that we use theory right now. So this is just an example of Titan at Triumph that did some measurements of these red nuclei here that we did not know before. And as you can see, when we do our simulations, it fundamentally changed our picture of the abundances here. So it's smoothing these out. This is something that people have noted within these solar abundances for a long time. They're oddly smooth in this region. And the more and more physics input that we're getting here, the more and more our simulations are starting to mock that up as well. So this is an example of how experiment can enter and help to modify our picture of what's going on within these events. Now, theory, however. So we will actually never ever be able to measure every single nucleus that's of relevance to our process. Won't happen. All right. So we do need theory to play a role. Right now we rely on theory, but nuclear theory is getting more and more advanced all the time. They've gotten to the point where they can build up from what they understand about fundamentals of quark interactions, the up quark, the down quark that make up the nucleus, and build up from there with very little in terms of parameters to adjust. So it's very fundamental ground up type work. So I have a colleague down the hallway from me at Triumph named Jason Holt, who does these kinds of fancy nuclear physics calculations that they call ab initio nuclear theory. So you can see in the NZ plane, previously ab initio was down here. These are very expensive computationally, these calculations. You can see here, this is that R process, where the R process tends to go in blue. And what we did was Jason and a postdoc of his, they were able to calculate the masses all along here in the third peak, like I told you about. So these are the first predictions of masses from ab initio nuclear theory in this region of relevance to gold, where they also predicted down here which species would no longer be stable and can't even hold on to a nucleus. So they went as far as they could with their calculations. It's a tremendous effort that they were able to achieve here. And so what did we get? When we put this within our nucleosynthesis calculations, this is what we get. So in the before, we had a third peak where gold lives that's very narrow. Within these neutron star merger conditions, you still have a lot of neutrons around. So you tend to capture because they're still around, and you can then push your peak in an uncomfortable way. Their masses changed that picture for us, their new masses, to the point where the way that they're spread out, they're less sensitive to these kinds of late time shifts. So that's something that has been debated in the past. Okay, could neutron star mergers really be the source of what we see in the Milky Way if they're always getting this very weird third peak? Well, the nuclear physics isn't known, and if you put in some theories, you don't get that very weird shift. Okay, so the last project that I want to talk about has to do with machine learning. So this is the newest thing that I've done that I think is really fun. And I also think that I built up your understanding to this point where we can talk about this. So as you can see up top are just a bunch of nucleosynthesis calculations with all types of variations in the astrophysics considered. These are all for the R process, the rapid neutron capture process. Down here is a bunch of astrophysics variations on what we call the slow neutron capture process. R process, S process, okay? So these are both things that are happening that we know can happen within astrophysics, and that they have very different looking patterns. So I explained to you how the nuclear physics is coming through in these peaks, for example. Where did my cursor go? Oh, here we go. In these peaks, for example, the nuclear physics is coming through. Similarly, for the S process, it's got different peaks because it interacts with those closed shells in different parts of the chart, okay? In different parts of the nuclear chart. So nevertheless, you can see that different processes have different patterns. Bottom line, different processes, different patterns. Now, down here, all these different colors are the patterns from a bunch of stars, all right? Here's your sun, but here are the patterns, the abundance patterns from a bunch of stars. So the leap that we made was, if machine learning, things like machine learning, can look at a picture and tell you that's a cat, that's a dog, that's a cat, that's a dog, they should absolutely be able to look at something like this and say, that's the S process, that's the R process. So we can feed it then the stars and have it organically tell us what it thinks enriched these stars. So this is what we aim to do. So this was work undertaken largely by my graduate student at UBC, Elin Wang, where effectively the first thing we did was a binary classifier. You tell it, hey, here's a sample of data that's R. Here's a sample of data that's S. These were our samples, but we let it know this is R, this is S. for a portion of the data. Then it trains on this data where it starts to analyze these trends. And eventually it was able to separate out what it thought was R process and what it thought was S process. Then it had never seen the stars before. It's entirely trained on just our nucleosynthesis calculations, theoretical calculations. Then we run the stars through this trained model and put on the plot where our model thinks they should go. So you can see there's a bunch of red stars here. So things that were previously labeled R process by these really simple ratios of like barium to europium type old school ways of classifying them are in red here. And ones that are in blue are labeled as S process currently. So what we were able to do is verify that, okay, our model is doing, pretty decently. It's matching the conventional labels most of the time. However, we're also seeing some cases where we do not agree with the conventional labels. And so what this could be is, in fact, these stars have been mislabeled. So these are things that if you go back and you look at the pattern, you can see, okay, maybe that was mislabeled through the very simple look at just two elements, where our machine learning takes into account more the full suite of how these patterns look. Okay, we also did something a bit more fancy called a one-class classifier, unsupervised learning. Effectively, this is something that's the way they put it is an autoencoder. So it's an encoder and a decoder. You encode over here, you decode. So you have an input, you try to get back out that output, and then you can look in the middle how it's condensed and looked at your data in a condensed fashion. And that's what this is. That's in this latent space, how it's condensed your data and looked at it. You can see a region that's R, a region that's S. And yet again, we are having things that are R and S occupy separate regions of the space. We are having the stars that are typically S lie in the typical S space, and the stars that are R in the typical R space. But again, we have a couple that are bleeding over within each other's categories. So we really feel that this is a path forward towards having a more rigorous way of classifying these stars by looking at the full pattern. Another, and the last thing that I'm gonna mention here is another cool aspect of this machine learning classification of stars is very recently a type of star that was believed to be R and S combinations was reclassified to say, okay, no, it couldn't be produced by any combination of R and S. It's actually coming from some kind of process in between the rapid neutron capture process and the slow neutron capture process that they so simply named the intermediate neutron capture process, or I process. So this is just an example where calculations have been done to show if you have something with a neutron density that's more corresponding to an I process rather than an R process, they're able to meet the abundance patterns of these kinds of stars. However, as an R process person, I would look at these papers and they very often grabbed a few R process patterns from the literature and said, impossible. It's impossible for it to be an R. So I always had this wonder, what if a deeper bench of R process calculations, a deeper set of R process calculations was considered? Would those stars then actually be considered to be R process stars? So we went ahead and we threw our machinery at these stars. Again, these are just our trained models. They have not seen the stars at all. And you can see the yellow are the I process stars. These are just some example I process calculations just to see where they lie in the space compared to the stars, but the stars are totally independent. So what we found is that essentially 2 out of 5 stars are probably in R or an S. They look like they're just in the R group, in the S group. They've just been misclassified because people weren't looking at a deep enough set of patterns, deep enough bench of patterns. However, 3 out of 5 of those stars that we looked at almost never wanted to identify as being S or R. So this is the first sort of independent confirmation from a machine learning toolkit that says, hey, okay, I don't think those can be S or R. Looks like something beyond the R and the S is going on here. Okay, so that's where I end, but I just wanted to highlight and walk us back through all the different branches, all the different things that our process connects to, all the different pieces that have to go into the R process in order to form this big picture. We talked about neutrino physics, we talked about experiment theory, we talked about time domain astronomy, stellar and galactic modeling, and finally machine learning. So there's a big spread of things that need to happen all together in order to better understand this picture. In other words, we need an interdisciplinary an interdisciplinary and international community that's working on this. And in fact, there's just numerous groups worldwide doing calculations, measurements, observations of relevance to heavy element synthesis. Things like the experimental campaigns at Triumph. We have the new aerial facility coming online soon. Advanced rare isotope laboratory. So we're going to have access to even more of these things, more beam time to explore their properties, advances in computational simulations. You saw that example of how even just 15 years ago, we had a different picture of what supernovae are doing. As computational simulations advance, we understand more and more what could be happening at these sites. We saw advances in nuclear theory as well and how they can change our picture, and of course, observational campaigns. So in this talk, I hope that I've taken you from the journey of the tiny, tiny neutrino all the way back through and to you, and how these elements have formed and just made us all, basically. So, okay, I just wanted to say thank you, and thanks again for having me.
So they're making gold now.
Yeah. Yeah.
I understood that all completely. Oops, sorry. That was wonderful.
Well, thank
Anybody
you.
have any questions?
Yeah.
No?
Yeah.
Yes.
If you could go back several billion years and look at the first star, would any of that be shown up?
Yeah, so yeah, not like the very earliest stars, but we do still have really old stars that have these signatures in
And do
there.
you see a difference between relatively new stars that have accumulated the debris from lots of other stars,
Yeah,
as
so
opposed to one that's quite old and
yes,
isolated?
yeah, these I had CNPI, okay, that stands for carbon enhanced metal poor. Essentially, when something's really metal poor, it doesn't have a lot of iron in it. And so this is something that we tend to say, okay, only one to few astrophysical events have created this particular picture because it doesn't have a lot of iron. The more and more you go over the course of things, the more and more you have a lot of different events that can produce iron. So something, for example, like our sun is absolutely a convolution of many, many, many events. But we can look at what we call metal poor stars that are very old and corresponding to just kind of one event. And there are some similar signatures that come through in those metal poor stars and in like our solar system stars as well. But yeah, we do comparisons there. Yes.
You mentioned stability in various key atomic numbers. Now, you did mention the SPDF shells in electrons.
Yeah.
Now, that determines chemical stability.
Yeah. Yeah.
I presume, and I have no clue if it's true, but I suspect, in a nucleus, there's some sort of quantum interference that makes certain structures stable versus unstable. Is that correct?
So
That's what you're getting?
yeah, your analogy is perfect. There's something called the nuclear shell model, which is essentially this idea that's analogous to the atom, the different levels that the electrons can occupy. You have different energy levels that different nucleons in a nucleus can occupy. And so when I say this is especially stable at this magic number of neutrons, it's actually at what we call a neutron shell closure. You filled up that particular shell. Very much in you can envision it as an analogy to what you said.
Gas. You look at nuclear.
Yeah, something like that. Something like that. That's perfect analogy.
So one thing that kind of slipped in and I kind of missed and felt just now in the discussion is that, okay, so you were looking at a certain types of stars that you believe are only produced from one event,
Mhm,
correct?
mhm.
Okay, so that's why there was this problem of a star that didn't seem to be one or the other.
Yeah,
Is that, but there's evidence that it only was a single event.
correct.
Whereas, because to me, the obvious thing was, well, okay, it's a mixture. But
So some
you're
of
saying
these, yeah.
that's not likely.
Actually, it's possible. You are correct that it's possible, and that is true, that there could be things that are a mixture. It's not clear if these represent one to few. I keep saying like one to few events, but we tend to assume that it's people in the field tend to assume it's just one and look at like one thing, but it could be a combination. What we did, however, is for a first step, if you ever wanted to look at combinations, you have to first build the framework that can understand the different distinct processes. And then it could maybe extrapolate towards putting them together in a more meaningful way. Because there are going to be some that are produced by one event. You could see many of them are falling just fine within an R process type of situation. So it's true, maybe some of these ones outside the R and the S could be a combination, but of what? Yeah, so that's work to be done.
One other question, and that is that okay, so you talk about R and S and they're different types of nuclear processes, correct?
Nucleosynthesis, yeah.
Yeah, okay. But why would you think that those would occur distinctly in different astrophysical events?
Because they do, yeah, they do from our modeling perspective, okay? So from a modeling perspective, when people look at AGB stars and they look at how that type of environment could have neutrons around, that is actually the site that people think that the S process is happening at, is within an AGB star, because you do have some dredge up where you can have some neutrons come through, and then within like your carbon oxygen type layer, you have things going on where you can capture on previous heavy seeds and produce the S process. So they are happening in different environments. I really wish I had the picture. Asymptotic giant branch. So yeah, you'd have to look at there's these, I could show you on a plot at some point. Yeah, exactly. Yeah, you'd have to look at an HR diagram, but basically it's that. So the S process operates pretty much near stability. So it's just capturing unstable species into slightly unstable species and moving along the valley of stability. So you see how there's very different peaks here? That's because it's hitting those magic numbers at different parts, all right? It would hit the magic numbers, the S process would hit the magic numbers here and here. So in order to even get an S process pattern, it has to be operating in a totally different part of the nuclear chart. And we can see that happen within simulations of different environments. So we simulate these environments, we see that it has what's capable of producing an S process. This R process, you need something that's really exotic, something explosive, something that's going to have a bunch of neutrons around and it's going to eject it quickly and it's going to eject a bunch of it. So you need very different kinds of conditions in order to get one versus the other. But we see signatures of both in stars. Yeah.
Great.